So we were doing buffer solutions, right? So I'm just going to try and open a few more questions related to buffer solutions. Case B. So let's try and solve this one. Okay, what do you think? He's saying that there's this asset, and he's saying that it's got two dissociation constants, right? K1 and K2, and suggest equations showing the two dissociations that give rise to the pKa values. But anyways, it's a, I mean, this acid like sulfuric acid, this one is a diprotic acid. Why is it a diprotic acid? Because if you, थोड़ा सा organic है, but if you look carefully, this is, it's got two carboxylic acid groups. In the middle, there's an alcohol, but it's got two carboxylic acid groups. So what it would do is it will produce two H plus lines. One H plus line will be produced by this carboxylic acid group. So that is going to release an H plus line. And the other H plus line would be produced by this one. I don't know if you remember, if you ever have a carboxylic acid, it has an OH, and that OH releases H positive ions. ठीक है, यही होता है. So you're saying write the equation for the two dissociations. So we're going to do just that. It's so remember the carboxylic acid is going to behave as I mean it's got CH OH, and then middle में there's another CHOH, and right at the end there's COOH. So it will dissociate and it will form. Well, it's going. I'm going to have to copy paste. It's such a long. So it will dissociate, and when it dissociates, one of the H is going to be lost from one side. So that is the first dissociation. And then you have the second dissociation, which is that the same diprotic acid. I'm going to just copy the whole equation. And paste. So the first one is lost already. And I mean, so this is already -1 to begin with. And now it's going to end up releasing another H. So you're going to have -1 on the other side as well. Okay, so that's your two dissociations. First, 1H. Either I'm going to write this down. So first 1H gets lost, and then the other H gets lost. Okay, so remember diprotic acids, they will have two dissociations. Ye clear? Is this clear to everyone?
Yes, sir.
Achha, but there's one very minor point, and that is that when I was explaining that there were two dissociations, I told you that the first dissociation is easy. I mean, the first dissociation, it's normally, because it's a neutral molecule, it's easier for it to lose an H plus ion. The second dissociation is already a negative ion. And if it's got a negative ion, it would be very difficult for it to lose a positive ion. So the positive ion would in fact be actually more attracted to it. It's not going to, I mean, it's very hard to produce a second H plus ion. So this is difficult dissociation. So that means the first K is going to have a large value because you're going to get more products, right? So K1 would be large and K2 is going to be small. Because the second dissociation is not going to happen and your product to reactant concentration ratio or the equilibrium constant for this one is going to come out to be small. So the reason I'm telling you this is that you also need to remember that if your K is large, always remember that your pK, the negative log would actually be smaller. Okay? So remember, if K is large, the negative log value is actually going to be, it's actually going to be smaller. So pKa would be small. And if your K is actually small, I mean, it's not dissociating, then your actual pKa value would come out to be large. Again, remember negative log ka ye tha कि negative log it changes everything. It is actually uh it actually bigger K means smaller pK, smaller K means bigger pK. So I just wanted to exactly match that our dissociations were right. This is the smaller pK value, so that means that's the first dissociation. So you have to write this equation, the one that we wrote down. And this is your bigger pK value. So that probably means the second association. And we wrote down the equation for the second association. Okay. So is this clear, this minor point at the end? Middle clear? Message Zag, Ibrahim, is this clear?
Yes.
Yes.
The isomers हम skip करें, we'll move to this. What is he saying? He's saying using the symbol HC to represent a prostate Lowry acid, right? Equation showing the substances behaving as bases. So they're going to accept H plus 9. So you got HC. NH3 would accept an H plus 9, it will become an H4 plus 1, and you'll be left with Z minus 1. This thing over here will also accept an H plus 9. So it will become CH3 OH2 plus 1 and Z minus 1. How do I know that this is capable of accepting H plus 9s is that anything that has lone pairs, if there is an H plus 9 floating around, it's capable of attracting it and it's capable of forming dative bonds with it. NH3 does exactly the same. Like you have NH3, it's got lone pairs, and there's an H plus 1 that's so it's capable of forming dative bonds with it. अच्छा दूसरे वाले में saying use the symbol B minus 1 to represent a base. So now you have to write equations showing them acting as acids. That means they're going to lose H plus 9s. So your base, which is B minus 1, will be the one that will be accepting H plus 9. So it's going to become NH2 minus 1, and the H is going to be lost, and it's going to get attracted to the B minus 1 because it's behaving as a base. I said because an H plus 1 is lost, therefore it's going to get a negative charge. I mean, whenever you lose something positive, you actually become negative. The second one, which H would be lost? The OHH would be lost. So it's going to become CH3O minus 1, and you're going to have HP. ये वाला भी clear है सारों को?
Yes.
Yes, sir.
अच्छा, so this one. Explain what is meant by a buffer solution. So it's a क्या था? It's a solution that will resist a change in pH. So it resists a change in pH when small amounts of acid or alkali are added to it. And the next part is now he's showing use equations to show how was the buffer solution formed. The buffer solution was formed when you had a weak acid and you had its conjugate base. You needed a base and an acid, a mixture of both. So over here, you've got HC and you got Z minus 1. It's basically, he has created a buffer. So he's created a buffer, and the buffer has the weak acid and it also has the conjugate base. So it's a mixture of both. So explain how the working of buffer relies on reversible reaction involving a processillary acid such as HC. So you're going to state that if acid is added, so that means you're adding H plus one. So who accepts it? Z minus one accepts it, and it becomes HC. So basically your equilibrium gets pushed backwards, right? So you're going to write that the equilibrium shifts to the left. And if base is added or alkali is added, so for example, you add OH minus one to it, then the acid is the one that's going to neutralize it. The H from the acid will react with the OH and it will form water, and you'll be left with C minus one. So in that case, the equilibrium shifts to the right. So your equilibrium that's going to shifts to the right. So I mean, those are typical questions. You're always going to get. So here's that buffer solution question, which says that. I mean, the first one, it's not a buffer solution question. He's just asking you to calculate the pH of propanoic acid. Which is what? Which is C2H5? COOH. Just hold on 1 second. So give me 1 minute, okay? I'll be back in 30 seconds. Chalin, going back to this question, you got, so we've got this propanoic acid. It's going to dissociate and it will form C2H5C O minus one, and it's going to release an H plus one. And the dissociation constant is the equilibrium constant for this reaction, which is C2H5CO minus one concentration times H plus one concentration divided by the weak acid concentration. Now remember, if it's just the weak acid, these two ions are going to have exactly the same concentration. So you can write your expression and you can change it to, you can simply change it to H plus one squared divided by the propanoic acid concentration. So I'm just going to write acid, right? So if it's just the weak acid, if it's not a buffer, so in this case, it's just a weak, you're being asked to calculate the pH. So you need to find out H plus one, which is going to be Ka times the acid concentration, and you would have to take the under root. If you rewrite the equation, you would have to take the under root. So your H plus one concentration would be, what is Ka? That's 1.34. So it's 1.34 times 10 power minus 5 times your acid concentration, which is also given, that's 0.5 mole per dm cube, and you have to take the under root as well. I think can somebody tell me what the answer to this is? Binal, Ibrahim, Hala,
2.6 times 10 to the power of -3.
2.6 times 10 power negative 3, right? And you can take the negative log, you'll get the pH. So what's the pH?
2.6.
Nahi, 2.6 hai?
Yes.
Check kar lo, can somebody else confirm? I don't think negative log of 2.6 times 10 power minus 3.
2.6 है.
बस ठीक है, पर 2.6 है. ठीक है. अच्छा नहीं, that's odd क्योंकि that means अच्छा चलो ठीक है, there was 2.6 over there, so didn't really make sense. But if the calculator is giving you that answer, then that's the answer. I said now the next part. Now the next part is a buffer solution F was prepared by adding 0.03 moles of sodium hydroxide to 100 cm cube of 0.5 mole per dm cube. So you got propanoic acid and he's adding sodium hydroxide to it and he's asking you to write the equation. So propanoic acid was C2H5, COH plus reacting it with NaOH. So my product is C2, H5CO minus 1, Na plus 1. That's my salt and water is going to be produced. Okay, so how many moles of NaOH? That's 0.03 moles. And how many moles of propanoic acid? ये कितना होगा? That's moles is what? Concentration times volume. So it's 0.5 into 100 or divided with 1000, right? कितना आ रहा है? Is that 0.05?
0.005.
नहीं, एक zero होगा.
Oh yes.
0.5.
5. Yeah.
ठीक है. So you're getting 0.05 moles, right? Achha, so you're seeing, well, I did this part earlier on, but part 3 is calculate the concentration of propanoic acid and sodium propanoid. So basically, he's asking you to calculate the concentration of this thing, and basically the acid and the conjugate base. So this is your conjugate base, and that's your acid. So now it's a limiting excess question. 0.03, it's 1:1, right? So 0.03 will completely react with 0.03. So that means over here, 0.02 moles will be left, right? 0.03 reacts with 0.03. And on the other side, it's going to produce how many moles? 0.03 moles and 0.03 moles of water, right? So फिर से एक दफा what's happening is that 0.03 moles react with 0.03 moles. So you're left with 0.02 and 0.03 react and they produce 0.03 of this and 0.03 of this other thing, right? So now what I have is I have the moles of propanoic acid that are left after the reaction. And I have the moles of sodium propanoid which is produced during the reaction. And now it's a buffer. Why is it a buffer? Because I have the solution now has the leftover weak acid and it also has the conjugate base, which is the salt. So now what he's asking for is not the moles, he's asking for the concentration of propanoic acid. So what is the formula of concentration? It's moles over volume, right? So the total volume of the solution that is given to us, that's 100 cm cube, right? Uh, in the middle, he's adding sodium hydroxide as well, but he didn't give us any volume for that. So that's probably being added in solid form. So the total solution, I guess, is 100 cm cube or 0.1 dm cube. So if I try and calculate the concentration, it's going to be 0.02 moles divided by 0.1 dm cube. And the other one would be the same as well, 0.03 moles Divide by 0.1 dm cube. What would that give me? It's going to give me, I think it's going to give me 0.3 mole per dm cube, right? Let me double check this one. This is probably going to give me 0.2 mole per dm cube. So, right, is this clear?
Yes.
And what was the buffer solution? Now he's asking you to calculate the pH of buffer solution. Now, in a buffer solution, the only difference was we already have the Ka. We have the acid concentration, which is the leftover acid in the solution. So we have that, right? And we have the conjugate base concentration. In a buffer, these two ions are not going to have exactly the same concentration because you actually ended up producing a lot of the base. So you're going to use the same expression, except that you're going to just plug in values and you're not going to make it H plus 1 squared. That's the only difference. So क्या था कि 1.34, I think it was 1.34 times 10 power minus 5. And you have, I'm focusing on that, you've got erythritine concentration, which is given over here, that's 0.3. And the bottom it's the propionic acid concentration, which is given as 0.2 and times H plus 1. So you just have to take 3 over 2 on the other side. And you don't even have to do under root. You just, what's 3 by 2 into 1.34? And then take the negative log as well.
The pH is 4.7.
PK, confirm color is everyone getting 4.7? So it's 4.7, right?
Yes, it's 4.7.
Okay. Now we're gonna move to the next thing now. TK, we just wanted to practice this a little bit. At the end, we'll do more past paper questions because we are still in the middle of the chapter. So we're gonna learn how to sketch pH curves now. So कहाँ पे गए? A to equilibrium. Do you guys remember K? I'm just going to summarize everything. This Ka is for weak acids, right? Weak acids are going to dissociate and you get this expression, which is product concentration divided by reactant concentration, right? The only difference is you just need to keep this in mind that if it's just a weak acid, these two ions will be produced in equal amounts. And you can write this as H plus 1 squared divided by the acid concentration. But if it's a buffer solution where they somehow produce these ions, then these two will not have the same concentration and you would have to go with the full expression. And in that case, this ion is normally coming from the salt that they are producing or that is being added. But anyway, so using the same things, using the same stuff, this was in AS as well. In AS, what you did was, pH curves or titration curves. So in AS, you were just supposed to sketch these pH curves. Now, what's going to happen is we have to know the exact values about when we are sketching these curves. So for example, number one, basically we're going to use the same concepts. It's just going to be a bit time consuming. So the first one is strong acid, strong base titration, right? So what would be the pH curve? And you have to tell them the exact values of the sketches, not just the sketches. So for example, I've got a burette and it has HCl in it. And that HCl is 0.1 mole per dm cube. Let's make it 0.2 mole per dm cube. And in the bottom, there's a flask which has NaOH. And that NaOH is has a concentration of, let's say, 0.15 mole per dm cube. Okay, so HCl and NaOH are reacting. We know what the reaction is. It's HCl plus NaOH, and it's going to produce. So it's going to produce NaCl plus H2O, right? So now, when you're plotting the titration curve, there are 3 points that you need to understand or plot. Point number one, I'm going to write those points. Point number one is you need to find or calculate the initial pH. Point number two is you're going to calculate the end point or the equivalence point. That is the volume of HCl that, I mean, that's basically the volume that needs to be added. Or you can say the tighter volume needed at the end point. Then finally, number three is you need to calculate the final pH. So I'm going to sketch a rough curve, but I'm going to give values, assign values to it. So this is the pH of the mixture on one axis. And on this side, it's the volume of HCl that's being added. And let's say in total, I'm adding the volume of NaOH I already know. That's, let's say that's 25 cm cube. So starting with the first thing, I need to know what the initial pH is. So my flask has this thing. So I need to know when I'm starting out, what is the pH right at the beginning. So that is something that I need to know. Now that's pretty easy. For strong bases, it's pretty easy. So starting pH. Okay, so initial pH, right? Well, your flask has NaOH and its concentration is 0.15 mole per dm cube. And since NaOH is a strong base, that also means that OH ions will also have exactly the same concentration. So OH ions, because it's going to fully dissociate, OH ion also has exactly the same concentration. So that's pretty easy. What I can do is I can calculate POH. I can take the negative log of the OH ion concentration. I say, okay, what do we get for negative log of 0.15?
0.82.
Okay, so we're getting 0.82. So that was the first thing we learned about calculating strong acids, strong bases. And since no one is interested in pOH, we had earlier learned that pH plus pOH is equal to 14, right? So that means my pH would be what? It would be 14 minus 0.82, which will come out to be 13 point what, 18? Okay, I guess that's 13.18. So that means my starting pH at right at the beginning is 13.18. Is that clear? Okay, that's where we're starting off. Because my flask only has NaOH. Clear, middle is Ibrahim, is this clear? Hala, is this clear?
Yeah.
Yes.
Yes.
Achha, so you started off with the initial pH, right? Now you need to find the equivalence point or the volume of HCl that is required. So for that we would need to know at what amount at what point will the NaOH get completely neutralized. So how many moles of NaOH do we have over here? I'm going to do volume times concentration. So kya hoga? That's going to be 0.15 times 25 or 0.025. How many moles do we get? 0.15 times,
3.75 times 10 power minus 3.
get that?
3.75 times 10 power minus 3.
So you're getting 3.75 times 10 power minus 3 moles, right? So the amount of HCl or the moles that need to be added for HCl, that's going to be exactly the same. It's 1:1, right? So you have the moles, you have the concentration. So what you can do is you can find the volume as well for HCl. So the volume would be 3.75. Yeah, moles is concentration times volume. Concentration times volume. So volume would be moles divided by concentration. So what moles do we have? We have 3.75, 10 power minus 3 moles. And you're going to go and divide this by 0.2 mole per dm cube.
0.019.
0.019. In cm cube, that's going to be 19 cm cube, right?
Yes.
You get 19 cm cube. So that means, I mean, focus on this axis. So that means when you add 19 cm cube, 19 cm cube must be somewhere over here. That is the equivalence point. That means all the NOH would probably get neutralized completely. And your pH at this point would be around 7, right? Because the NOH would be, because you're adding the right amount of, the exact or the required amount of HCl, which is 19 cm cube required, right? So that's your equivalence point. Is that clear?
Yes.
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 Yes, in other words, it's also referred to as the uh, neutralization point. Achha, so would probably be close to pH 7. As a reason you don't call it the neutralization point is that it's normally not exactly 7. So equivalence point is a better word. Now the final thing is, because my sketch is not complete, the graph says 50 cm cube of HCl. So that means what I need to do is, what would be the pH if 50 cm cube of HCl is added, right? So that means this is the amount of HCl that's completely in excess. So how much excess HCl are we adding? If I end up adding, I mean, if I don't stop at 19 and I keep adding, so that means I'm adding excess HCl, which should be the 19 and 50, 31 cm cube of excess HCl, right? And I know the concentration of that HCl, so that's 31 divided by 1,000 times, we know the HCl concentration that we are adding from the top, that's 0.2 mole per dm cube. So how many moles in excess have we added? Yeah, what's 31 divided by 1,000 into 0.2?
6.2 times 10 power minus 3.
Moles, right? Now, I also need to find the concentration of this excess HCl because eventually I would need to find the pH, right? And remember, since it's HCl, the HCl and H plus 1 concentration would be exactly the same. So I need to find the concentration. So the moles of this HCl will be divided by the volume of the solution. The volume of the solution is 75 cm cube because you had 25 cm cube of NaOH already in the flask. And from the top, you're adding 50 more aqueous solution of HCl, right? So what would be the total volume of the solution at the end? These two solutions are going to mix up. And the total solution, so you clear 25, you had 25 cm cube already initially. And from the top, you added 50 more. So that means the leftover HCl that you have in the flask is now present in 75 cm cube solution, which is 0.075 dm cube, right? तो क्या आ रहा है? What's the concentration of this HCl?
0.082.
0.82 mole per dm cube. And since HCl is a strong acid, the H plus one will also have the same concentration, so you can calculate the pH then for this. I mean, take the negative log off. So what is the pH that we are getting?
One point one.
It's coming out to be 1.1. So that means so the final pH would be 1.1. Achha, so I'm just going to repeat everything quickly. You had NaOH in the flask, that was your initial pH. The concentration of NaOH was given, so you basically had the concentration of OH ions, and all you had to do was you take the negative log of that, you'll get POH, and from POH you can get pH, right? And then you calculated the equivalence point, the point at which it should be neutralized. That came out to be 19 cm cube. You knew the moles, so the same amount of moles was supposed to be added from the top, and you were able to calculate the volume, right? And then the graph showed that you were adding 50 cm cubes. So that means you were adding a lot of excess HCl, right? So we were able to figure out that there was 31 cm cube of excess HCl, which came out to be these many moles. And since the two solutions are now combined into one solution at the end, so the total volume of the solution is 75 cm cube, and we were able to figure out the concentration and then eventually the pH as well. Ye clear hai सारों को? Is this clear?
Yes.
So the one last thing is that there are 3 points. The pH curve normally doesn't really move much. Most of the pH movement happens around the equivalence point. Around the equivalence point, the curve is pretty much straight. So around the equivalence, the curve is pretty much straight, and so before that, the pH barely moves, and after the equivalence point, the pH barely moves. Most of the transition in pH or the change in pH happens around the equivalence point. Okay, so this is how you're going to sketch. It's always going to be an S-shaped curve. You're going to measure the first point, the equivalence point, and the uh, final pH of the whole titration, and then you're going to sketch the curve. Okay, is this clear?
Yes.
So, we'll do more questions like this, sketching pH curves. And we just did strong acid and strong bases at the moment. We're going to do, next we're going to do weak acids and weak bases as well, okay? Okay, everyone.